Here we are for our final section in Chapter 12 on vectors. If you haven't used vectors before, you will be using them in physics. I don't know exactly where it falls in the curriculum. I know when I was in high school it was like the end of the year. So vectors. Why is it important to understand the inverse of a matrix? So we're going to use those inverses not only to solve systems of equations, but also for vectors. We're going to use basic vector operations of rotation, addition, subtraction, and scalar multiplication. We're going to use the dot product to determine if vectors are perpendicular. So a vector is in two dimensions. A vector has magnitude and direction. You can describe a vector as a directed line segment with initial and terminal points. So a vector is kind of like a ray. It has a starting point and an ending point, but it has an arrow on the end. Same magnitude and direction represent this same vector. So here I have v equals pq, where p is 1, 1, and q is 3, 4, and v equals rs, where r is negative 1, 2, and s is 1, 5. If we look at them, they both have the same rise over run of 3 over 2. So these represent the same vector, just in two different locations. So as long as they're same dimensions, and they don't have to be the same starting point or ending point. They can still be the same vectors. So vocabulary. A vector has both direction and magnitude, and you often use an arrow to represent a vector. So when I saw this, I thought of Despicable Me and the villain of Vector, because he's committing crime with both direction and magnitude. Hopefully you've seen the movie. If you haven't, you should go watch it after your math lesson, of course. The magnitude of a vector, denoted by v, is the length of the arrow, and you can denote it as the absolute value of v, because the length is always positive, or the magnitude is always positive. You can't have a negative magnitude. You show the direction of the vector by the initial point and terminal point of the arrow. So it starts at a point, ends at an arrow. Alright, representing a vector. What is the component form of the vector v equals pq shown here? So I have this one, this vector. P is at 1, 2, and q is at 8, 5. So what we're trying to do is find out how long this is. So our goal is to put this at the origin. So if we were to move point P to the origin, here we go, directionally we'd have to go left 1 and down 2. So we're going to take those coordinates. To move it left, is that an x value or is that a y value? Well, that's an x value. So we have to do p equals 1 minus 1 and 2 minus 2. That gives us our new p point at 0, 0. Now whatever we do to p, we also have to do to q. So q equals 8 minus 1 and 5 minus 2. So our new q is 8 minus 1 is 7, 5 minus 2 is 3. So that's our new terminal point. Now we use that terminal point to write a vector. When we write vectors, we use not parentheses, but we use these little like pointy bracket things to denote that's a vector. So it goes 7 units left and 3 units up. Or 7 units right, 7 units right and 3 units up. Which you can see from P to Q, you can count 7 right and 3 up from one point to the other. Okay, let's do another one. We have two vectors here. We have T and U and R and S. So let's go ahead and do R and S really quick. So our goal is to get from here to here. So we'd have to go left 1, or right 1. Left. I'm sorry. If you didn't know, I am directionally challenged. And then we have to move from 4 down 4. So whatever we do to R, we also have to do to S. So negative 2 plus 1 and negative 2 minus 4. So our new terminal point for our vector is negative 1 plus negative 2 plus 1 is negative 1. Negative 2 minus 4 more is negative 6. So that's the vector for RS. And then we do the same thing with TU. we have to go down 1, left 2, so subtract 2. That vector would be 5 minus 2 is 3, and 5 minus 1 is 4. 3, 4. Pretty simple. Okay, operations with vectors. If you're given that you have vector v, v1, v2, and vector w, w1, w2, and any real number k, if you add v plus w, you just add your points or your values that are in the same place, so your 1s and your 2s. If you subtract, you do the same thing. You subtract your 1s, subtract your 2s. Oh, that second one's supposed to say w. If you multiply by a scalar, you just multiply everything inside. So I'm not going to really go over that because that's pretty easy. Add x values together, add y values together, subtract x values, subtract y values, multiply by a scalar. We've done these so many times. There you go. So what it means when you multiply by scalars, you're making 2 of the same thing you had before. Okay. Let u equal -2, 3, and v equal 5, -2. What is the absolute value of u plus v? So this is different than just adding. This has the absolute value, and we're going to round it to the nearest hundredth. So what we do first is to find u plus v, we use the tip to tail method. So from the end of our first one, u to v, or u at -2, 3, then we add v, 5, -2, and see where we end up. So we're going to draw u in standard position, and then at the tip of u, we're going to draw v, and then figure out what the terminal of u at 2v is. I think there's component form. Okay. So let me draw this for you really quick. Okay, so here u is from here to here, and then 5, 1, 2, 3, 4, 5, and down 2. Yep. So this one's u, and this one's v. So our terminal point, the one where it ends at the second place, is the point 2, 1. You see how we did that? So from the origin, go left 2, up 3, and then from there, go right 5 and down 2. Now we're going to use that point 3, 1, and we're going to add the squares of both of those together and take the square root of that. So it's kind of weird. So we look at where u plus v ended, add the squares of the points, and then square root those. So you get 3.16. And then you can check by plugging it back in, and you get 3, 1. So if we did u minus v, same rules apply, except instead of 3 squared plus 1 squared, we do 3 squared minus 1 squared. And 9 minus 1 is 8, and the square root of 8 is 2.83. So that's what you should get for that one. Okay, for scalar multiplication. So we have v and 3v. So they want us to graph that. So if v is 1, -2, there's 1v. If we wanted to do 3 of those, we go right and down 2 more, and right and down 2 more. So we're making it 3 times as long. So there's the graph of that vector. And as you can see, they both ended on 3, -6. So for -2, you just multiply -2 to each of the values, and there's that one. Instead of going up and to the right, it goes down to the left. Alright, there's a couple more. I want you to work on those. And then the last one is finding dot products. So if v equals v1, v2, and w equals w1, w2, the dot product of v times w, you multiply your first values in each of them, and then you add the second values of each of them. If you multiply them together and you get 0, then your two vectors are perpendicular. So let's look at this one. t equals 2, -5, and u equals 7, 3. So in order to find this one, you take your first values, 2 times 7, which is 14, and then you add your second values, -5 times 3, which is -15, and you get -1. Well, we didn't get 0, so that means it is not perpendicular. Okay, and then we have this one. 2 times 10 is 20, minus 4 times 5, which is 20. Oh wait, I forgot a negative somewhere. That's supposed to be negative. Is that what happened? Yes. Oh, okay, that's okay. I'm just losing my mind. No big deal. So that's supposed to be a -5. Sorry about that. So then you should get 0. So 10, 4, and 2, and -5. These vectors are perpendicular to each other. And if you remember from geometry, perpendicular means that they're opposite reciprocals. They cross at 90-degree angles. Alright, and that's it. Hope you have a great night.